Hello, everybody. Welcome again to this second day of our API workshop. I hope you enjoy all the discussion we had yesterday, and you will enjoy those of today. I'm not sure we have the agenda here on the, but we are starting now with the first keynote, and maybe I let Manolis introduce the keynote.
Right. Hello, everybody. We get started with our keynote speaker, Denis Dutoit, from the side of SEA List. Denis' position is Senior Program Manager at SEA for Advanced Computing and Digital Architectures, and has a particular interest in what we can call pathfinding, which is pretty much looking forward into designs, implications, and has a particular interest in chiplet-based designs. So given his track record in prior projects, etc., I think he has been spot on in assigning, let's say, priority to certain trends. So I look forward to this presentation. And we are grateful to have him over as a speaker.
I would just say that I remind Denis as part of Mont Blanc 2 review, defending the idea of chiplet, and the reviewer was a bit skeptic about it, saying nobody does that. And right now, they wouldn't say that.
Okay, thank you, Manolis and Etienne, for the short introduction. And thank you again for the dinner yesterday. It was once again quite fine. So I will talk about chiplet and interposer. That's a subject I have been working on for a long time, more than 10 years ago. And just to say that we have started to work together on chiplets because with the more than 10 years ago with the Hexanode project, this is really the origin of European chiplet for high performance computing. We have, in the framework of this project, Hexanode, we have designed and manufactured a chiplet in the Alps between CEA, ETH Zurich, and ST. And this chiplet and the complete hardware platform has been validated here in Crete in Force. So 10 years ago already, we worked on this subject, and we succeed in stacking several dies on a system in package or multi-chip modules. And one of these ICs was a 2D IC with chiplet, the one you can see here, chiplet stacked on an interposer. So the story is not new. Now, at that time, chiplets were in, let's say, development, in R&D. Now, chiplets are really in the industry, and we will see the different configuration, state-of-the-art of chiplet technology, especially for CPU and GPUs. Okay, so what is a chiplet? Let's just start with one definition. So in 2010, a chiplet was a small chips. Let's say if you do a Google search before 2010, you will see this kind of on photo, on picture. And now a chiplet, this is the let's say the definition we have on Wikipedia. So a chiplet is a tiny integrated circuit. So that's right. Often chiplets are smaller, let's say, than a monolithic system on chips. Contains a well-defined subset of functionality. So during this presentation, I will show you that chiplet could be, let's say, disaggregated. This is the term we use as several functions, but also as several structural die like SRAM and logic. So this is not totally true. It is designed to be combined with other chiplet and an interposer in a single package, so that's right. But the combination involves packaging technologies. We will see that during this presentation, but the combination of chiplets also involves new die-to-die interfaces, and we will have a look on the different type of interfaces we have today for chiplets. And a set of chiplet can be implemented in a mixed and match Lego-like assembly. So that's right, but it is not so easy as it is written here. You may understand that when you want to design chiplets, you have challenges to overcome. And with a few examples, because at CA we have designed several demonstrators based on chiplets. And from this example, I will try to show you that there are some challenges in chiplet design, and I will describe how we have solved these challenges. And finally, chiplet is a research subject, because if you have a look on the IEEE Explore site, you will see that there is an exploding number of papers with a chiplet in the titles. Okay, that's also a keyword, but anyway, there are lots of new papers talking about chiplets. Okay, so during this presentation, first of all, I will provide a brief history since the start of API. Then I will go to a kind of, let's say, perhaps a kind of tutorial about chiplets with a few words about disaggregation, which is more or less architecture partitioning. Then once you have disaggregated your system on chip, now you have to put all your chiplets together. And for that, you need advanced package technology. I will go through that a little bit. And also die-to-die interfaces. We will see the landscape of die-to-die interfaces for chiplet. Then we will go through architecture and design solutions with 3 examples. Active interposer for high performance computing, photonic interposer for scale up, and let's say standard package for automotive, because chiplet is not only chips for high performance computing, but also chips with more reasonable packaging technology like the one you use for automotive. Then I will end the presentation with a kind of personal statement on Europe's position in the chiplet marketplace, just to have a look on the European landscape and how I believe that chiplets is an opportunity for increased European sovereignty. And I will end with a perspective about chiplets for the next decade. Okay, so I have 45, okay, yeah. So I have plenty of slides. Perhaps I will go quite quickly for some of them, but let's start like this. Okay, so let's start with a brief history in the start of API. Okay, I used to show this plot about the performances of let's say the top one of supercomputer from the top 500 list. And this slide has been presented during the first UPI tutorial in 2019. And this slide is showing, first of all, the performance improvement or the compute performance improvement of the supercomputer in blue. And it shows as well the energy per operation, more or less the energy efficiency of each operation in green. What we can see is the pace of, let's say, performance improvement, which is 1 order of magnitude every 4 years. So that's what the status in 2019. So what's happened since since the launch of API? So I have put here in red the different performances from top 500 list, the performances of the top 1 supercomputer. So what we can see is that, and it's interesting to have a look at that it's really challenging to sustain the trend that we observed over the last 20 years. For performance, for pure performance, expressed in let's say, dual precision flow per second, that's more or less okay. But we can see that for energy efficiency or for energy per operation, it's really, really difficult to achieve the trends we have observed over the past decades. And it's very clear that today we can improve the performance, pure performance, computing performance of the supercomputer, but at the price of more power of the total system. So it shows really these trends. Okay, so this is not the subject of this keynote, but just to notice that's important to see. Okay, so what do we had? So what was the state of the art at the start of EPI? So when we started EPI, the top one was a Summit supercomputer with 2 chips. So we had already a heterogeneous or hybrid architecture with CPU and GPU. The CPU was the IBM Power 9. So that's a really classical CPU, a big monolithic die, as IBM is very good to design in 14 nanometer. And for the GPU, it was already NVIDIA one with already some advanced packaging technologies. That was 2.5D. We will see, but 2.5D means that you put together several dies on a substrate, on a silicon substrate. We call it interposer. Then the first chip that was, let's say, introduced during the EPI project was the CPU from Fujitsu. It was the ARM introduction within this HPC world. There was only one chip, the CPU one, and in terms of packaging technologies, that was also 2.5D integration with HBM2 and the CPU on the same interposer. Then we get, I think it was the first exascale supercomputer. And for this one, we appeared system in package based chiplet. And this is the CPU from AMD. Okay, this one, you can see the chiplet concept. It's very clear with this picture, with the different, I will put the laser pointer here. Okay, that's a very good example of chiplet architecture with an I/O chiplet in the middle and several compute chiplets in order to perform the complete performance of the chip. And it's a system in package, no, let's say, silicon interposer for this solution. And the GPU, AMD based, it's okay. We have 2 dies, but 2 very large dies in the same socket. We can call them chiplet, but the dies are so large that it's difficult to call it a chiplet. But anyway, it's let's say a use case we often have in a chiplet design with duplication of the die in order to improve the performances or the density of the computation. And finally, what we have today, still chiplets for the CPU with the I/O die and the CPU dies. I don't remember, but for this one, AMD made also 3D integration with a cache, SRAM cache, on top of the processor die. And introduction of 3D integration with several chiplets stacked on the base die. So that's really the concept I showed you just at the beginning of the presentation of the Hexanode with a base die with peripheral network on chips and some, let's say, a communication infrastructure. On top of it, we stacked a processor die. So it's really vertical integration. And as soon as we have vertical integration, we call it 3D. Okay, so we can say that the last decade was the chiplet decade, and HPC compute node performance has been strongly driven by the chiplet and 3D integration. So since the beginning of API, chiplets is really a technology that has emerged and that has been industrialized and that has made the performance we have today with the supercomputer. Okay, so now I will go into some details and some explanation of what is architecture partitioning, what we call also disaggregation. Okay, I often say that we have two types, let's say, of disaggregation, structural one and functional one. Regarding structural one, here is the evolution of the Moore's law, the theoretical evolution of the Moore's law. This is a graph I've made a few years ago, but it is still valid. Okay, you have twice the density at each generation of technology, and each generation of technology node is coming every 2 years. That's basic Moore's law. What we observe is the following, is that in fact, there is a slowdown of the new technology introduction because technologies, advanced nodes are more and more complicated to handle. For example, for 2 nanometers, we will have backside power delivery, which is another nightmare in terms of power distribution network. So each time we have a new technology, we need to work on some design solutions for this new technology. So it means that we have a slowdown of this new technology introduction. Something which is also important to say is that the shrinking, let's say the shrink factor, depending on the part of the chip, is not the same. I mean that this is, for example, with a chip with 50% of logic, 35% of SRAM, and 15 of analog, which is more or less the normal ratio for a system on chip. Then you can see that the logic is shrinking quite well, let's say, each technology. So it's really useful to use new technology for logic. But for analog, you don't need a new technology. You will not gain a lot in terms of area with analog. And this is more or less the same with SRAM. It means that we are going to divide a system on chip, into several, let's say, structural die that could be SRAM, logic, and analog. So we have what I call a disaggregated system on chip with structural chiplets. And this is really an advantage in terms of, let's say, cost, because since you have smaller die, you have higher yield. It means that at the end, the cost is less. You can also use the right technology for the right structural die, logic, analog, and SRAM. At the end, you have a higher number of transistors per package and a reduced cost per transistor. So let's say that today, one of the partitioning is structural, mainly for cost reason, just to get a reduced cost per transistors. Because if you use advanced technology node for analog cells, that okay, you will lose money, let's say. There is another type of disaggregation. I call it functional. Let's have the HPC case. Okay, this yesterday, Craig showed us this slide just to explain a little bit the trends in terms of architecture for HPC compute node. So we started with the monocore architecture. Then when we reach the frequency wall, we go to parallelism with several processors working at a lower, let's say, frequency. But there was the power consumption wall. That's why we have defined heterogeneous architecture, so that part of the code or part of the application has been specialized within hardware accelerator in order to gain in terms of power efficiency. And then today we reach, let's say, the reticle size. I mean that okay, that's you have very, very big chips, and that's really, really complicated to design those chips. And now we are much more disaggregating the chips, the system on chip, into several functional dies. Once again, there is a need of scale in and scale out. We have new type of interconnect. This is another story. But anyway, the trend today is to just to disaggregate your CPU and GPU into functional chiplets. For example, a general purpose CPU, an IO chiplet, or an accelerator. And what is also let's say the beauty of the chiplet concept, if you have a very symmetric architecture for the accelerator or for general purpose CPU, as explained by Craig yesterday, for example, with 80 CPU, 80 core CPU, you can, for example, cut it into 4 with 20 cores CPU chiplets. So this partitioning is mainly here for flexibility and for performance scalability, for also reuse of some of the chiplets. Sometimes you don't have let's say, for a new generation, you don't have to redo the complete design. You can perhaps just redesign your accelerator, and then the generation after redesign your I/O. So it means that with this concept and functional partitioning, you get lots of flexibility for your design. Just a few examples. So some of the slides are coming from people that were presented, during the chiplet summit. By the way, if you want to know about chiplets, technical topics, design, marketplace, you can go to the chiplet summit in California. The next one is in end of February. It's the same date of ISSCC, but anyway, you can have a very, very good overview of the chiplet marketplace during this conference. So this slide has been presented by Palo Alto Electron 2 years ago, and it shows different kind of functional disaggregation. So the one I talked about with the disaggregation of a monolithic die into several functional chiplets, as shown here, and obviously with interfaces in between, with communication in between, and the uniform chiplet partitioning, for example, SMP-like partitioning with an identical chiplet you duplicate in order to gain in terms of performance. And this duplication of chiplet could be done horizontally or side by side, or you can do it also 3D, going verticals with several chiplets with a vertical communication, exactly like the high bandwidth memory with the memory plane. Here you can have some different compute plane with 3D integration and vertical communication in between the what we call the layers or the tiers. Okay, so that's disaggregation. Let's go down. So you have divided your chip. You have plenty of chiplets. Now, obviously, at the end, you need a system. And this system, so you need aggregation thanks to packaging technologies and also die-to-die interface. Just a few, once again, a slide that has been presented during the chiplet summit, just to show you the landscape of the different packaging technologies and the terminology. When we combine together several chiplets side by side in a multi-chip module or in a system in package, this is what we call 2D packaging. So that's really standard packaging. Another first advanced packaging technologies is 2.5D. When you put together two chiplets, for example, this one on a silicon interposer, that's 2.5D integration. The silicon interposer is just there for communication, for metal layers, nothing else. And another type of advanced packaging technology is what we call bridge. The communication between the two chiplets is just made on a very small piece of silicon interposer. The rest of the system of the substrate is organic one. the classic one. And then we have really 3D ICs, exactly the same we saw at the beginning of the presentation. When you stack chiplet, or for example, compute chiplet, on top of an active silicon base die, which embed, for example, communication infrastructure, peripheral interfaces, and so on. Okay, so I think that you have understood that interface and package choice are linked for signal integrity reason. For example, you cannot use a highly parallel interface on laminate because the pitch on organic substrate is not sufficient. So this is the evolution of the different packaging technologies. Normal system in package, more advanced. We call it fan-out, then interposer, and then 3D integration. And each time you use an advanced packaging technology, first of all, you evolved of interfaces. You can start with the classical one, I2C, SPI, LVDS, and then ultra short reach, bunch of wire, UCIe, AIB. So plenty of interfaces. And just you have to understand that when you use advanced packaging technology like 2.5D and 3D, then the pitch is smaller, so you have a higher bandwidth because you can put more wires, and you use interfaces such as UCIe and VC or a bunch of wires. Okay, so packaging technologies. Okay, I don't think I will go through all the possible package. I've made a first overview just before. What you have to understand that system architects must choose between a quite large panel of technologies. So it depends your power, performance, area, and cost targets. So today, 2.5D is a standard for advanced packaging technology. 3D adoption is growing, and there are new markets like photonics and CPOs that are emerging as really strong drivers of advanced packaging technology. And often we combine several technologies when we want to aggregate chiplets technology. And I used to say as well that there is a new, let's say, a new way of working, or a new level of or a new stage of design with the system design with chiplet technology. So how do you disaggregate your SOC, and then what kind of technology you use to reaggregate everything thanks to advanced packaging? Just as an illustration, I put here the little bit marketing about CLT. A little bit. I've put here the different integration technologies that are developed at CLT. What the message here is that you have plenty of, as I said before, you have plenty of technologies. You can go down to less than 1 micrometer pitch. With some technology, for example, hybrid bonding technology. In the middle here, this is the technology we use for the Hexanode project, with micro bumps in between the two layers of chiplet, in between the active interposer, so the base die, and the compute chiplet. Okay, you still have die level packaging, which is, for example, for some IoT or automotive applications. This is a kind of package you can use. Same for this one, for automotive. This one is the one which is used today for HPC, for CPU, GPU. We had, I think, with AMD and the Vcache, the first hybrid bonding integration in the industrial world. And this is a more aggressive pitch technology. Okay, so just a few examples. How we use advanced packaging technologies and chiplet for all demonstrators. So active interposer for HPC. The interposer could be also a way to embed some waveguides. So we have what we call a photonic interposer, and we can map within the interposer, instead of mapping, let's say, network on chip on the active interposer where you have logic, we can map in the interposer some waveguides in order to have an optical network on chip to communicate in between the chiplets. And for quantum technologies as well, for cryogenic electronics, we use also the interposer concept and chiplet concept. Okay, just to say that hybrid bonding is now the reference for advanced system for high density and high bandwidth. So the pitch is now going, so the pitch will go below 1 micrometer in between two wires. But anyway, we work also on relaxed pitch for other type of application. So just perhaps you may have understood that when you have 2 layers of silicon of chips, if you want to go to the top die, you need to go through the bottom one, and for that you have to do holes. Let's say we call it through silicon via. So you cannot use advanced packaging without these technological bricks, which is a TSV. And when you improve the pitch of your connection in between the two dies, you have also to improve the pitch of the TSV, and that's not so easy. And that's why people are also on technological side. People are also working on high density TSV to be able to propagate all signals from one level of die to the other one. And just one slide about glass interposer. The issue with silicon interposer is that they are processed at wafer level, and it's quite costly. Now people are working and are developing a new substrate based on glass, and they are manufactured at panel level, like the PCB, like the organic substrate. So the cost is it's less expensive, and okay, that's promising. Perhaps that will be the next generation of substrate, and CLT is also working to make sure that hybrid bonding could be also be used for glass interposer. Okay, now I will go through the die-to-die interface. Okay, so you have understood that chiplets have to communicate together. There are plenty of die-to-die interface. I think that we were one of the first one to propose 3D interfaces. We call it 3D plug, and then there was several let's say interface coming. I think that one of the first interface was the AIB. 10 years ago, DARPA launched a big project to define interfaces for chiplets, and Intel has developed the AIB, and they are trying to let's say push it within an alliance. And then I think that there was the bunch of wire for Open Compute project, and now the one which is really emerging and which is with lots of advance is UCIe. So anyway, and we still have the let's say ultra short reach interfaces based on SerDes. So just to say that there are plenty of interfaces. Some of them are open standard, like bunch of wire and UCIe, but it's difficult. We'll go a little bit through all of them. Today we cannot say that we have one interface that everybody is using. I will show you where we are today. Okay, what is important when you want to choose a die-to-die? It's obviously the bandwidth, gigabit per second, the latency, because you once again, when you do chiplet partitioning with identical chiplet and SMP, the processors have to, the latency is really important in between the different chiplets. So that's why latency is one of the major KPI for selecting a die-to-die interface. Energy efficiency. Once again, if you disaggregate your system, so you have several advantages, but if you lose all of these advantages with a big and power-consuming interface. So you lose all of your gain of the chiplet concept. So picojoule per bit and milliwatt. That's really also important KPI for die to die. The reach of the interface. And in order to compare die-to-die interface, we often use this KPI, gigabit per second, bandwidth per square millimeter, or bandwidth per millimeter, which is the beachfront bandwidth, so that you can compare several interfaces. So for the EPI, we've made this work within the work package 11. So for people working on EPI, don't hesitate to go through this deliverable. We've made this table with a comparison between different type of interfaces, ultra short reach, bundle of wires, AIB, UCIe, and Open HBI as well, which is a derivative of HBM interfaces. And if you want to design a new interface, the model has been made so that you let's say enter your target, for example, 1 terabit per second, and then it computes the number of lanes, the number of modules for each type of interface with some estimates, of some KPIs, right? Like picojoule per bit, milliwatt, and so on. So that's a tool that you can use if you want to select an interface for your design. It provides you with a very, very first exploration. That's not something which is very precise, but at least it could be used to do a first selection in between several possibilities. Okay, what is important for die-to-die is interoperability. Often people are saying that if two die-to-die are interoperable in terms of, let's say, mechanical aspect and electrical aspect, I would like to say that this is not sufficient. That is to say that the PHY compatibility is important, okay, but there are other level of interoperability. First of all, the data link one. So you have to let's say to communicate with identical packet organization. That's needed compatibility, and obviously protocol and transport layer have to be compatible, because if you send a AXI stream on another chip which rely only on CHI streams, they will not work. So it's really important to have a full range of compatibility at file level, data link level, and protocol and transport level. This is not because your interface is UCIe compatible that you'll be able to plug any UCIe chiplets. You need also to think about data link and protocol layers. A little focus on UCIe, because we believe within EPI that UCIe is one of, that's a really good specification because lots of people are working on it, and it's let's say the one with the more, let's say, more complete, with lots of new features that each time, each release, they introduce new features, not only communication, mechanical and electrical, but also new features about manageability, about the design from manufacturing, debug, and so on. So that's really the more, let's say, industrial one. Okay, UCIe is made by layers with physical layers, die-to-die adapter, and the protocol layers. So the UCIe more or less is compatible with CXL, PCI Express, or any streaming interface. Once again, there is a full software stack for UCIe, up to reliability, availability, and serviceability. So that's really the more industrial interface. And UCAE, people would like to use UCAE for automotive to get a common interface for such a market. And UCAE, there is a special working group within the UCAE standardization body for automotive. And UCAE is also a good way to go to 3D, to go to a vertical connection with the first specification of a vertical link, because for vertical link you really you need as well to define the matrix, the pitch, the electrical compatibility, and so on. So a new standard with this UCAE 3D. Okay, so I've made an overview of the possible packaging technologies, an overview of the possible interfaces in between the different chiplets. I would like to go through now some example of architecture and design solution with an active interposer, photonic interposer, and standard package for automotive. So in our lab, we've worked on co-optimization between technology and architecture to try to gain an order of magnitude in terms of energy efficiency and bandwidth efficiency, thanks to 2D integration and chiplet and heterogeneous integration. So from this compute node made of discrete components, we've worked on different type of integration, memory and logic, logic and logic, heterogeneous integration with hexanode, and also photonic interposer or active interposer. And each time with an objective for power efficiency or bandwidth efficiency. Just an example of, quite quickly, an example on active interposer. So this is a demonstrator we've done. It's called Intact, of 6 chiplets stacked on an interposer. The interposer is exactly the same as the hexanode one, but the chiplet is not the same. Once again, this is a way to show you that we can design an interposer, an active one, and design several chiplets, and you can mix and match Lego-like. Since you have the same footprint between the different chiplets, you can do some Lego-like architecture. And that's a good example of 2 different chiplets, one developed within hexanode and one developed here. Okay, so the goal was really to demonstrate that it's possible to interconnect in 3D chiplets, compute chiplets with processor cores, level 1, level 2 of memory onto an active interposer with distributed network on chip, power management as well, and some interfaces for the memories. And you have the view of the communication between the active interposer and the chiplet. Just an example, a real example of a layout and design of these 2D interfaces. Very, very simple for this one, because the distance in between the 2 chips is very, very short. So buffers and protection and level, the protection here. For a chiplet design, you need to adapt your flow, your design flow. You cannot develop chiplet with the current design flow. So it means new tools or tools that has to be adapted for 3D design. Okay, new tools are at architecture level. For example, for co-design, for simulation, architecture simulation, also for architecture exploration, tools at physical implementation level with a new LVS and design rule checker, new DFT type, 3D physical design. So quite a lot of tools at 3D implementation stage, and obviously at sign off when you design chiplets, you need to make sign-offs in terms of airdrop, thermal validation, LVSDRC, obviously, and also chip package sign-off. Okay, we worked in close cooperation with 3D CAD tools vendors through some collaborative projects to make sure that the 3D design tools will be ready when chiplet, or they are already there, but for chiplet design right now. And just two examples. One that we have, let's say, stage tools, yeah. Flow, we have worked with Mentor and Siemens on co-design, because this is a co-design workshop, so chiplet is also plenty of co-design process. This one is co-design for package on die-to-package interaction. So we worked with Mentor thanks to our test vehicles, the one I described, the intact one, to work together for this co-design, to build these co-design tools. And we developed as well our own tools. So you know quite well VPSIM. So this is always co-design, but co-design at system level. So co-design could be at several levels. Before it was at physical level with a package, and here at system level, when we, as I said previously, when we disaggregate your architecture and aggregate again, then you have to simulate everything, and that's the role of the VPSIM you used for API, and also some automatic exploration that we have developed. Okay, so that's an example of tools and flow we need to set up for 3D design. There are also other topics. I will let the slide, but for example, DFT is different. So that's okay, plenty of possibilities. Just I will go quite quick on photonic interposer, just to say that there is a hype for co-package optics, and co-package optics really need advanced packaging technologies. And in our lab, we are working on scale-up based on a photonic interposer, and the communication in between the chiplets are made thanks to waveguides within the interposer here in red. So that's our demonstrator we have developed, which is shown here. And we would like next generation to disaggregate this optical network chip into several components in order to avoid a very large silicon interposer or photonic interposer, which is quite costly. Okay, so that's just an example. That's a complete new design because the network on chip is now optical. That's new routing. Okay, everything has to be done. And let's just have a look on the picture. So we've made what we call a morphological demonstrator to make sure that the assembly is good. Next step is to have a smallest demonstrator to check the electrical and photonic aspects. That's a long project with several intermediate steps to check everything one by one. Okay, just a word about automotive. There are lots of chiplet initiatives for automotive. You may know that the electrical and electronical architecture of automotive will evolve to a central compute that could embed chiplet architecture. So we had a project with a big OEM. They had let's say several range of cars, several range of electronics, and it was too costly for them in terms of NRE to design, for example, here nine chips. So they asked us, how do you see, what do you think about chiplets? And we have together, we have defined, in fact, only 3 chiplets. And if you aggregate, so we have disaggregated the complete, the 9, let's say, chips. We have disaggregated them into 3 chiplets and reaggregating everything with 4 packaging, standard and advanced package, so that at the end, we can reconstruct the 9 architectures. But this is really a good example of the power of chiplets by merging and disaggregating as simple as possible with several chiplets in order to gain and to reuse chiplets among the different architecture. Okay, so just I would like to end this presentation with, let's say, a personal statement about Europe's position in the chiplet marketplace. Very quickly, the marketplace today for chiplets is really on servers and HPC. Second market is PC. You can see with the Ryzen and AMD chips and CPU. Then automotive, and then mobile phone. So as you can see, if you had server and PCs, that's quite the major marketplace for chiplets, a little bit for automotive and mobile phone. In fact, chiplets are already there, but with internal solutions for computing giants. This slide has been made 1 or 2 years ago, so perhaps it's not so up to date, but anyway, Intel, AMD, Apple, Amazon, Tesla, they are all their own chiplet-based architecture, with their own protocol in between. And that's true that today, let's say 1/3 of the design starts with chiplets in mind. And in the coming years, more than half of the design will start with chiplets. And this is my view of the chiplet marketplace today. We have a galaxy of major players capturing the market with their own protocol. That's true with NVIDIA with NVLink, AMD with Infinite Fabric, and Intel with IAB. So that they have their own protocol for HPC server and PC markets, and they are all sharing the same IP providers, foundries, except Intel, and all that. So that's the big players are here. The chiplet market is here, but completely closed. And some people are trying to, there is a nebula of initiative to leverage open chiplet marketplace, but that's really difficult to leverage this open market. That's my view today, where we are in terms of chiplet marketplace. So the European landscape, first of all, I think that there is a central role of RTOs for this, for the chiplet, for the future of chiplet. I've listed here two major initiatives, one from Fraunhofer, the Chiplet Center of Excellence, and one from IMEC, the Automotive Chiplet Program. At CEA, this is not really our business model, let's say, to have this kind of initiative. So what we are more doing, that we have lots of experience in a chiplet design. So we contribute to several chiplet projects or to, let's say, bilateral cooperation with our industrial partners. But we are, even if it's not in the press, we are quite active in the chiplet arena. That's perhaps this is not exhaustive, but this is my what I see myself in terms of European landscape around the chiplet projects. So first of all, I think that EuroHPC was the first one and pioneered heterogeneous integration. So the chiplet was not the purpose, is not the purpose of the project, but heterogeneous integration is one of the objectives. It was the objective, the primary objective for Hexanode, and it was also objective for Mont Blanc 2020, EPI, and there. So that's, I think, the first project around heterogeneous integration on chiplets. Today, ChipGU is just starting to propose a project with chiplets. So I know a project that has just started a packaging project, E2 Pacman. This is a packaging project, but we have some use cases with chiplets for computing for embedded market, not for HPC. And coming soon, it's in the underground negotiation. Coming soon, a big project for chiplet for automotive should start before end of this year. So it's just ramping up at the chip GU level. And today, for the European Defense Fund, there is an ongoing call for chiplet for defense. So let's say Europe started with HPC, then with embedded application with the chip GU, and it will then continue with the chiplets for defense. So that's progressively, step by step, we have some funding for chiplet design. So I think that's really an opportunity to increase sovereignty. I will go through this one, but just to explain why chiplet will improve sovereignty, European sovereignty, I would like just to explain the difference in terms of supply chain between single die, so classical one, IP design, chip design, manufacturing, assembly, and test, and with the one of multi-die, let's say, system or chiplet system, with obviously IP design, chiplet manufacturing for any chiplets, but you have an additional step, which is assembly, test, and packaging for the complete system, starting from what we call non-good die. Obviously, in between, you need a common interface. So why and what are the opportunities to regain sovereignty in Europe with chiplets? First of all, if you, let's say, have in mind two kind of chiplets, one with advanced technology node and one with mature technology node, then you can more or less design your, for example, accelerator, IP, chiplet, manufacturing, and integration within a European fab, while for advanced technology node, you cannot manufacture it in Europe, but at least to have the fabless design here in Europe. And this is what we've done for EPI, because the EPAC test chip has been, let's say, designed and manufactured in Europe. And for general purpose processor REA, the design has been made in Europe. And the manufacturing, oops, it's a little mistake. The manufacturing, not in Europe, but anyway, that's a way for accelerator to make it and to have a fully sovereign supply chain, and for the general purpose processor to have at least the design in Europe. Okay, so what is still missing in Europe? The advanced technology fab, obviously, the assembly. We do not have any of that in Europe. The IP design and the die-to-die interface IP, which is especially for advanced technology, not yet in Europe. Okay, so that's what is missing. So to conclude, the perspective, chiplet is just an enablement. And I think that in the next decades, we will have plenty of new technologies in order to improve density, and also to have a low power. And today, the trend is very clear for compute, a mixed advanced technology node with mature node for accelerators, for example. On memory, there are plenty of emerging memories, ReRAM, MRAM, FILRAM, and plenty new DRAMs as well. New concept like in-memory computing, new type of components like high bandwidth flash, and for the interconnect, all what is related to scale out and scale up will certainly be done in optical. That includes, for example, optical switch. So we do not have any chiplet here, but for me, chiplet and interposer are really the keys for all integration of all this new technology. So we will certainly have in the next years plenty of new chiplets, heterogeneous chiplets. So power management chiplets, that's really an issue now due to the high power consumption of the chips. Optical I/O chiplets, emerging memory chiplets, you can perhaps stack, you can side by side or stack on top, like the Vcache, stack on top of the processor, and application-specific chiplet for some acceleration. We certainly will see new technology for interposer like photonic one or glass one, and new challenge for integration, so memory on processor. What about thermal aspect for that? Power delivery network with regulators and optical communication with switch. So I would like to end this presentation saying that research and development on chiplet, interposer, and integration is really far from complete. And in order to continue to pursue this work, we obviously need co-design. Okay, so thank you all. I would like to thank all the CEA team working on integration, and also the architecture and design and simulation team from LIST working on the design and simulation, and all the projects that been funded with the logo you can see here. So thanks for your attention.
Questions or comments for the speaker?
Denis, thank you very much. At the beginning, you told us that logic, SRAM, and analog have different scaling characteristics, and that analog does not benefit too much from small nodes, I guess because they want accuracy for the transistor, so they need large transistors. But SRAM and logic, in my mind, they are the same thing. So somewhere I'm not, where am I mistaken? Why do they differ, logic and SRAM?
SRAM design, I think that it's more and more difficult to pack, let's say, transistors. And for the SRAM memory node, it seems that the design rules for SRAM is not evolving at the same pace of design rules for logic. And it's more difficult to pack all the transistors in a memory node. You need to handle variability. Okay, you have perhaps new issue with SRAM, so that it's a little bit bigger. And this is my my feeling.
Other questions for the speaker? Well, I have a short question, Denis. You showed the comparison table for the various die-to-die technologies, and I noticed it had the concept of beachfront, which I think is important to compare the technologies. So do you think that UCIe is on a good path towards that, shall we say, criterion?
Yeah, but for several reasons, because UCA is not one standard, it's several one. Each one adapted to the substrate. And it is made to be as simple as possible. But anyway, at the end, you have lots of layers, and it's more and more complex. But today, this is for me the one which is the most promising, let's say.
Promising. Okay. Okay. Yes.
Hello, Denis. Thanks for the nice presentation. Maybe just a forward-looking question, again, about UCIe. You showed that one of the, actually several biggest players have some of their own solutions where they keep their markets kind of closed. How do you see, or do you see that they will open to some UCIe-like solutions so that their dies can be integrated with any kind of die that complies to the new standard, or they are going to still try to enforce their own solutions to keep the market kind of closed?
I think that they will open them, but if you use their standard, you will have to use their CPU or GPU. So that's I don't think that it will be fully open, let's say. That's yeah. So you will be able, perhaps, if you use Infinity Fabric, so you will be able to design chiplets compatible with AMD chips, but you'll have to use AMD chips. You will not be you cannot use, for example, Infinity Fabrics for your own, let's say, chiplet design. So it will not be completely open for if you use their let's say their other chip. I don't know how to express that, but
Yes, you mentioned the fact that it can be a chance for Europe, and I fully agree, and we have to search for that. What in your mind could be the main obstacle on having a good EU ecosystem permitting easily to combine chiplet from different provider and to in a Lego-like way, as you mentioned, and to have more easily a custom solution adapted for such or such use case. And the question after, what could be the way for us in Europe to move forward in this direction?
yeah, that's not so simple. At the beginning of EPI, we said, okay, we have to impose to propose a solution to everybody. In the meantime, there were lots of new possible solutions, new possible standards. So now I would say up to us and to Europe to select one of them and to make sure that everybody is able to design with such interface. So having the IP portfolio and so all what is needed to design such kind of system with the chosen interface. So today, I will say we need really a push to choose and to choose together a standard one, and to make sure that we have funding to develop the infrastructure around this interface. That's my personal view.
Further questions or comments for the speaker from any of the remote attendees? Okay, if not, let's thank Denis for this excellent keynote. So we can take a short break, roughly 15 minutes for a refreshment, and then we have two contributors from remote. So please be back in around 15 minutes. Thank you.